So I changed the colors here to show that these are two p orbitals with an opposite phase or an opposite sign. So what happens when we add a 2pa and we subtract from it 2pxb, or the same with a 2pya, subtracting a 2pyb, is that we're actually going to cancel out the wave function in the center. So we now have two nodal planes. So again, this is an antibonding orbital, and what you see is that there is now less electron density between the two nuclei than there was when you had non-bonding. So we're going to call this the sigma 2px star, or if we're talking about the 2py orbitals, we'll call this the pi 2px star and the pi 2py star. And the pi star orbitals result from any time you have destructive interference from two p orbitals that are either the px or the py. So now we can move on to an example where we do, in fact, have to use some p orbitals. So this would be B2. How many electrons are in boron? 5. I see some hands going up. There's 5 electrons. So what you'll notice here is that I only filled in 3 electrons. What do these electrons represent? Valence electrons. Okay, so sometimes you're going to be asked to draw a molecular orbital diagram where you're asked to include all electrons, and sometimes it will specifically say only include valence electrons. That happens because of space issues, that you are asked to do that, because you can always assume that all of the core orbitals are already going to be filled. So in this case, we're just drawing the molecular orbital diagram for the valence electrons, so we have 3 for each. And what we see here is now when we're combining the p, we have our 2px and our 2py pi orbitals that are lower in energy, and then our pi antibonding orbitals that are higher in energy. You might be asking where the 2pz orbital is, and we'll get to that soon once we need it. Let's just first fill in this for the B2 case. So we can start at the bottom, 2 electrons in sigma 2s, 2 electrons in sigma 2s star. Now we need to jump up to using these pi orbitals. And what we're going to do is put 1 electron into each of our pi 2px and 2py orbitals. So again, you can see as we're filling up our molecular orbitals, we're using the exact same principle we used to fill up atomic orbitals. So let's think about what the valence electron configuration is here. So now we're looking at the case of B2. And what we're looking at is a valence electron molecular orbital diagram. So let's just draw the electron configuration for the valence orbitals. So that will be sigma 2s, 2, sigma 2s star, 2. And now we start in with our pi 2px, 1, and our pi 2py, 1. So this is our valence electron configuration for B2. All right, so what would you expect the bonding order for B2 to be? Shout it out if you know. 1. Oh, and I didn't write it up there, but it is 1, and we can see that it's 1 because it's 1/2 of 2, 4 minus 2, so 1/2 of 2, the bonding order is going to be equal to 1.